right. So I'm starting over. Yeah. Okay. So we're starting on gas laws, and as we went over last week, just before we left for the weekend, we talked about what are the different things we can use to describe gases. Gases in a container or gases just around in the atmosphere. And so we came up with 4 different things. The volume, how much space that gas is taking up, which would be kind of difficult to get if it weren't in a container. So like we could get the volume of gas in this room because this room is like a container, right? So I can measure the width and the length and the height of the room and get a volume for how much air is in here. And I could do the same thing for a beaker or for a balloon. A balloon would be a little bit more math because it's round and not perfectly, it's not like a perfect sphere or anything. But I could calculate that volume. So if you have a container with gas inside of it, you can figure out how much space that gas is taking up. That's your volume. I can measure the temperature, how hot or cold it is. And remember, there's going to be several different temperatures. We'll get to that later. Today, we're not going to talk about temperature, but we will talk about the different types of temperature. Number of moles, which if you remember, moles is literally just a count of atoms. So 1 mole has Avogadro's number of atoms inside of it. So when I tell you how many moles are inside the balloon, I'm telling you literally how many atoms are inside the balloon, which is a better way to do weight, because we started with weight. And as we kind of saw with the scale and a balloon, it's hard to weigh air. It's hard to weigh a gas, no matter what it's contained in. So the number of moles is going to be a better way to present that. And then finally, pressure. How much is that gas being squeezed? Or is it not being squeezed at all? The pressure is going to help you determine kind of how it's confined. And so those are the 4 things that we're looking here: volume, temperature, pressure, and moles, which are shown by V, T, P, and N for moles. So remember, moles is not M, it's the letter N. And we started by putting all that together into one formula, which we said was PV equals nRT. And then I showed you how we could rearrange that and kind of think of the balloon as balloon number 1 before I changed something, and then balloon number 2 after I changed it. I either added more air, I squeezed it a little bit, or I did something to it to kind of change what its numbers would be. And when we did that, we ended up with P1 V1 over N1. Oh wait, that's just a 1. N1 T1 is equal to P2 V2 over N2 T2. These are our overarching equations. We will not get to these yet. This is technically called the ideal gas law, which will be one of the later assignments. This one is technically called the combined gas law, which again will be later. But you'll see as we go through each one of these, you're going to use just a part of these particular equations. We got this to turn into that. And so technically, if I use part of this, I'm also using part of this. I'm just thinking about it in a different way. So when we come back over here to our gas laws, we're looking at volume, temperature, number of moles, and pressure. And those are going to define the behavior of a gas. Remember, gases are always moving. And so if they're doing something, if they're active, the way we kind of describe that is the word behavior. That sounds weird because we usually use behavior for things that are conscious and thinking and like choosing to do those things. But it still applies for gases. So a gas law is just a law that shows the relationship between 2 or more properties of a gas. So for each of these gas laws, we're pretty much just going to pick part of this. A bunch of them are only going to be 2 numbers. Sometimes we mix in 3 or 4. It just depends on the gas law. But we're going to start off with just 2 of these for this particular one. So instead of using this whole equation, P1 V1 over N1 T1 equals P2 V2 over N2 T2, we're just going to use the parts that we need. If we don't use anything else, if they don't tell us about moles and temperature, I'm just going to erase those and ignore it. So you'll see in a second when we get our equation, it's a part of that overall equation. Now, a couple things. We've introduced this a little bit back in the electromagnetic spectrum, but I want everybody to kind of see it again. We have 2 different ways this is going to work. It's either going to be directly proportional, and directly proportional means they're the same. If one of them goes up, the other one goes up. If one of them goes down, the other one goes down. They're going to get bigger and smaller together. That's directly proportional. Does that make sense? So if I increase one, I'm going to increase the other one. Inversely proportional is the opposite. If it's the inverse, yeah, one's going to go up, the other one's going to go down. And if I raise one of them, the other one's going to go down. So, I mean, they go up and down either way. But know that they're opposite in inverse, and they're the same in directly proportional. And so that will also help you out, because sometimes you get some numbers, you pop them in the calculator, you get an answer, and you want to know, is this the right answer before? So using these, you can kind of figure out, hey, should my answer get bigger or should it get smaller? Because I'm raising this thing, should my answer go up and get bigger because it's directly proportional? Or if I'm raising this thing, should my answer go down and get smaller because it's inversely proportional? So this kind of helps you just double check your answers and make sure you're going in the right direction. When a variable is not included in gas law, it is assumed to be held constant, and we don't have to worry about it. So for Boyle's law, he's going to talk about pressure and volume. Those are the two things that Boyle worries about, and that's what's in his law. So for moles and temperature, we assume they stay the same. We assume that whatever air is in my balloon doesn't change temperature, and I don't change how much molecules are inside. So I can just ignore those, and they're not part of the equation. So that's what the last bullet point's telling us. If it's not discussed, we assume that it's constant, and we don't really use it. So Boyle's law deals with pressure and volume. We're pretty comfortable with volume. We're going to talk about pressure for just a second because, actually, we'll get to pressure in a minute. I thought they were going to start with pressure. Know that pressure is how much something is being squeezed. Pressure is the force applied per unit of area. Gas particles apply pressure on surfaces they come into contact with. And here's what it is. Why, if there's so much empty space in between molecules of gas, I think I shoved it all in here. Here it is. Hold on. My bad. All right. Ready now. So we talked about what gases are doing the other day. And so like inside this balloon, I got a lot of little particles, like a whole bunch of little particles that are kind of everywhere, but there's a whole bunch of empty space in between them. It's mostly empty space in here, right? Now, why, if this is mostly empty space, is the balloon this big? If it's empty space, shouldn't the balloon squeeze the empty space and make it smaller, right? So what's actually pushing this balloon out if all this empty space is here? Well, it's the molecules, because what are the molecules doing? What are the molecules always doing, and they never stop doing? They're moving. So literally, every time one of these molecules is moving and it hits the edge of the balloon, it's pushing the balloon out. And so that's what pushes the balloon back out. When I push in, something's pushing back out. That's those molecules hitting the edge. That's what causes my pressure. The more the molecules hit the edge, the more pressure I have. If they're not hitting the edge very much, then I'm not going to have very much pressure at all. And that's the way that pressure works. And so, know when we talk about pressure, it's all about how much your molecules are moving, how fast they're moving can apply, but it's the overall kinetic energy because it's their size too. So it's not just the speed, it's also the size.
How fast do they move?
We can actually calculate that. We'll get into that soon. So we do talk about speed at some point in time. But the speeds are, the speeds are not things that really make us understand better because they're not on the same scale as normal speeds that we're used to. It's not like a 60 mile an hour atom.
Is it really fast?
We'll look at it. We'll look at it. I haven't done the math recently.
Really fast and really slow.
It's faster than you think it's going to be. I mean, if it's fast enough for those little atoms to be keeping the balloon up, it's going to be faster than normal objects. But not like speed of light fast or anything like that.
Slower than light, but faster than a car.
Yeah. Well, you'll see. You'll do the math. You'll see. So look, Boyle's law. This is the one we're working on today. Boyle's law at a constant temperature and amount of gas. So right at the front, Boyle's law tells us that the temperature doesn't change and the number of moles doesn't change. I'm keeping those two the same. They're constant. At a constant temperature and amount of gas, The pressure and volume of an ideal gas are inversely proportional. What does inverse mean? Yes, up and down opposite. So if I raise the pressure, what's going to happen to my volume?
It's gonna go down.
It's going to go down. If I raise the volume, what's going to happen to the pressure? It's going to go down. So they're going to go opposite of each other, and they illustrate that here. As volume increases, gas particles collide with the container walls less frequently. So basically, I have all my atoms bouncing around inside this balloon. If I don't put any more atoms in, so normally, how do you make a balloon bigger?
Blow air into it.
You got to blow air into it. What if there's some way I could make the balloon bigger without putting more air into it? Then the atoms that are in here, they have more space to travel before they hit the edge of the balloon. And so that's why if I increase my volume, now my atoms are hitting the side of my container less often and the pressure goes down. If I squeeze the balloon and make the volume less, now all these molecules are in a smaller space and they're going to hit the walls much more often. That's going to increase my pressure. And so that's what we're looking at when we're comparing our pressure and our volume. Let's see. And then they say the same thing. When volume decreases, gas particles collide more frequently with the container walls, results in increasing pressure. Now, we got this little video. This is going to illustrate it. So you have your beaker, and all these molecules are just going to be bouncing around. As soon as I hit play, you'll see that the pressure's low. What they're going to do is push this plunger down. So they're not adding any more air, and no air can escape. It's sealed up. So the same amount of molecules are always in here. But once this plunger goes down, I reduce the space that they have. They're all going to travel the same speed, but they're going to hit the plunger in the sides of the walls more often, which increases the pressure. So just watch that happen real quick. So they're bouncing around. The plunger goes down. They're not going any faster, but now they're hitting the sides of the container much more often because they have less room to move around. And so the pressure has gone up. And so volume has gone down, pressure has gone up. Now we're seeing the relationship between these two. So here's our formula. Like I said, it's the same as we have up there on the combined gas law. P1V1 over N1T1 equals P2V2 over N2T2. But I've gotten rid of the moles and temperature because I don't need it. And so this is my new formula for Boyle's law. It's P1V1 equals P2V2. And the kicker here is, for every problem, they're going to give you 3 of these numbers. And they're going to leave off the 4th. And your job is to plug in those 3 numbers and solve for the 4th one. So, for example, real quick, let's say they give me pressure 1 and volume 1, and they give me pressure 2. I need to get volume 2 by itself. I'm solving for volume 2. What am I going to do with this pressure 2 to get it to the other side?
Divide by P.
I got to divide by. I divide by specifically P2. So if I divide by P2 on both sides, I end up with P2, P2, and those P2s on the left side can cancel out, right? So I got that here, and then these P2s cancel out, and all I'm left with is V2 is equal to P1, V1 divided by P2. So the math here should be pretty simple as long as you know to divide to move something over to the other side. I'm going to reset this. And the hardest part really, I think, is figuring out what's your 1s and what's your 2s. Most of the time they kind of put them together, but sometimes they make it a little bit tricky. So let's see if they give us some examples. Oh no, now we get to the pressure stuff. The good news is liters is usually going to be your volume. They're very rarely going to give you gallons or cubic centimeters or anything like that. If you have trouble converting, let me know. For the pressure, you're going to have to convert pretty often. And they go ahead and give this to you. I'm going to write it on the board. It's also on your study sheet whenever you get your study sheet. But your pressure is this. 1 atmosphere. Where's my marker? Actually, that's not the marker. This is. Let me write it down here. There we go. You give me that back. 1 ATM. ATM stands for atmospheres, not ATMs like we think of ATMs. 1 atmosphere is equal to 760 millimeters mercury and 101.3 kilopascals. So all of these are ways that we measure temperature. And this is basically an equivalency. What you want to do with this, remember mole ratios with B over A. And I put the thing on bottom that I want to get rid of, and I put the thing on top that I want to get into. You're going to make the same thing with these just to convert. So like if I have, let me erase this. If I have, let's say 2.3 atmospheres, and they want me to turn it into millimeters mercury, right? I'm just going to make a ratio with atmospheres on the bottom and millimeters mercury on the top. So when I do that, I end up with 760 millimeters mercury over 1 atmosphere. And that's going to be my conversion factor. So if I take this, multiply by 760, I don't really need to divide by 1, but I don't know that until I set this up. That's going to be how many millimeters mercury I have. So you're going to have to convert between these sometimes. If you need help with that, just let me know. Coach Kumba, did I say start on the assignment?
Yeah.
You think you're special or something? Okay, so listen. You're going to have to convert between pressures sometimes. If you don't, good for you. You're lucky. If you do, it's just something you got to do sometimes. So here's an example problem. The initial pressure. So is initial going to be 1 or 2?
1.
Initial is going to be 1. So this is my P1, right? Everybody make sure you're paying attention, heads up, looking at the board. P1 is 3.0 liters. Sample of gas was at 2.5 atmospheres. So if it's in the same sentence as my P1, I can assume this is what as my, oh wait, never mind. Let's read this again. What is this number right here? What's the unit? Liters, which is volume. So this is actually my V1 right here. And then my pressure over here, we know that atmospheres is a pressure. This is my P1. So I have V1, P1, and then at what pressure will the volume of the gas expand to 5 liters? What is this one?
That's the V2.
This is my V2. So now I know what I have, and what am I searching for? P2. I'm looking for P2. They give me P1 and V1 and V2, and I'm looking for P2. So all I have to do is plug these in and do the little math. So look at this over here. Let me actually do it on the bottom of this board. So I have P1 times V1. So I have 2.5 atmospheres times 3.0 liters is equal to, what do we got? 5.0 liters times P2, right? So what am I solving for? What am I trying to get by itself? The P2, what do I do with the 5.0 liters? I divide by it and I move it over to the other side. I erase this on this side, and now what's my math I got to do? 2.5 times 3, divide by 5. That's it. That's my answer. And so when I do that, they set everything up. I don't need to convert. They have it set up just like I do. And yes, 1.5 atmospheres is my answer. They got one more example. Don't start yet. What is the initial pressure? Well, so they tell me the initial pressure of a 0.127 liter sample of gas was 198.7 kilopascals. At what volume will the pressure of the gas be? 263.9 kilopascals. So give me pressure on both of these. They give me volume 1. This time I'm solving for what? V2. So I set up the problem just the same. I'm going to multiply my number ones. So I'm going to have 0.127, where are we at? 0.127 liters times 198.7 kilopascals is equal to 263.9 kilopascals times V2. Divide by this on both sides. 263.9 kilopascals. This gets erased. and I end up with just V2 is equal to this. Multiply the top two numbers, divide by the bottom number, and you should be good to go. So note, and it doesn't really matter how you arrange this, whether you're solving for volume or whether you're solving for pressure, what mathematically are you always doing? You're always multiplying the top two numbers and dividing by one bottom number. That should be, for this particular assignment, it should always be this same format. And so I believe
We're ready.
that's the last one. It's not assigned yet, so give me just a second to assign it. But yes, you can open your Chromebooks and go ahead and get started on it. You'll need a calculator.
Yeah, what did Columbia see during the day?
Ethan, I got your calculator, bro. Don't even worry. Not Adrian, but I got you.
You're not trying to think.
Hold on a second. Are you raising your hand?
Me
Yeah,
too,
go ahead.
me too.
Anyone else?
That was best. Thank you. You only need three. One for me, one for I, one for Mike. I'm doing that in my head.
Okay, it's open. How many questions?
16. 15.
16. That ain't too bad. That ain't too bad.
15 questions. A lot.
So be working on it.
I'm not finishing.
20 minutes ain't too bad. Yes, there go.
That's almost like
Yeah. Where's it? Oh. No. You got 4 answers and 4 questions. So what they want you to do on that one is just convert these. So you're going to use your conversions over here. So let me actually come over here. What number is that? Number 1. So remember what I did over here. Whatever it is, you're going to use this setup to convert things. You're going to start with your number. So like, what's your top number A or letter A? What do they want you to convert? 394.8. It's mmHg. So that's your millimeters mercury. So you have 398 mmHg. And then to convert, I want to use these numbers. And what are you trying to convert to? Atmospheres. So you want mmHg on the bottom, atmospheres on the top, and you use these numbers. So it's just like B over A in my mole ratio. The one I want to get rid of goes on bottom, 760 mmHg. Oops, I messed that up, but and then 1 atmosphere. So to convert from millimeters mercury to atmospheres, all you need to do is divide by 760, right? So I'm taking my number times 1, which doesn't do anything, divide by 760. That should be my answers because millimeters mercury is now gone, and my units are atmospheres.
What should we round to?
Give me 2 numbers past the decimal usually. Or on those, maybe just give me the same number of decimals as you started with. So if they give you 1 number past the decimal, maybe just give them 1 number past the decimal. Sapling gets a little iffy sometimes on that. Rid of KPAs and get into atmospheres. That's going to be your setup there. Whatever your number is, it's probably not 398. Your number. Is it on the top or the bottom? So if it's on the top of this fraction, you multiply. If it's on the bottom, you divide. So for this one, if you're going from KPAs to atmospheres, you're going to take your number and then divide by 101.3.
What about atmosphere to mmHg?
Okay, so
yeah, that's what I was.
atmospheres is what you're getting rid of, right? So this goes on bottom of the fraction. And mmHg is what you're getting into. That goes on top of the fraction. So the fraction you're multiplying by should be 760 over 1. Yeah, make it quick. It's kind of warm in here. Are y'all cold?
Yeah, it is a little chilly.
I said the opposite.
Oh, well then yeah, I agree with you.
So mmHg to pascals, you're gonna have to do both. So like, look at this. If it's mmHg to pascals, so remember, these are the numbers you're using to convert. So if I'm going, am I still recording? Yeah. If I'm going from mmHg to pascals, or does it say kilopascals or pascals? Just pascals. Okay. Well, that's a little different because these are kilopascals. So if they were regular pascals, what does kilo stand for? 1,000. So regular pascals would be 101,300 pascals. Does that make sense? Because kilo stands for 1,000. So that's the number we're going to use. So if you're getting rid of millimeters mercury, 760 needs to go on the bottom, and then pascals would go on the top, which is 101,300. Or, not to confuse, you would just use the kilopascals number and then multiply by 1,000 to get rid of the kilo. Because kilo stands for 1,000. Yeah, it is going to be a big number because you're multiplying by like 100,000. And so it should be a pretty big number. Yeah, you are dividing by 760, but the 101,000 is a lot bigger. And if it's millimeters mercury, you're probably starting with a pretty big millimeters mercury number. Yeah.
Seems a little bit harder.
Yeah, millimeters mercury is usually in the hundreds, and then atmospheres is usually in like the single digits. Because like 5 atmospheres above you is quite a bit of atmospheres. Yeah, converting in between these units is something they throw in to make it harder. Home. Get the same instruction. The same instruction. So look, when you end up on number 5, they say a sample of ideal gas at 100.7 kPa. So kPa is pressure. And a volume of 1609 milliliters. That's volume. So this is my P1. This is my V1. And they tell me they take that gas and they place it in a weighted balloon and drop it into the ocean. What's the ocean going to do the further you go down? Yeah, the pressure increases. And you feel that like if you dive to the bottom of a swimming pool, you can feel the pressure in your ears just a little way. So as this balloon drops to the bottom of the ocean, it's going to get squeezed. So as the sample descends, the water pressure compresses the balloon and reduces its volume. It's squeezing it. When the pressure has increased to this, there's my P2. So I have P1, V1, P2. They ask me, what is the V2? What is the volume of the sample? Assume that the temperature was held constant. And I don't need to convert because both of my pressures are in kilopascals. Both my volumes are in milliliters. So I'm going to use these numbers just like they're given to me. Plug this in for P1, plug that in for V1, plug that in for P2, and solve for V2. And you should be able to get to the answer, just like we were doing on the board there. And if you get stuck, let me know. Okay, for those of y'all that are at home, I hope this helped you out a little bit. I'm going to go ahead and end the video here and post it online. If you have questions, please send me an email. Let me know, and I will do my best to get you an answer pretty quickly. Thank you. Have a nice day.